Now, the question was, in the 1980s, could earthquakes like those happen here? And as we mentioned with defining prehistory as anything before written records say much about this territory, it would be hard to say from the this map is compiled in 1720 in France for the King of France, and they have Spanish intelligence from voyages of Vizcaíno and Cabrillo up the California coast as far as Cape Blanco. But then this is all just unknown territory farther to the northwest. So, but everything else looks very familiar on this map. It's pretty amazing. Okay, so for our subduction zone, though, it's pretty well recognized now that we have these very big earthquakes that, and that the patch that breaks is something like that. But the geophysical enigma in the 1980s was whether this patch in here with the North America plate removed, this red patch over here becomes, in cartoon form, this patch here, whether the rocks were sliding past one another in some benign fashion, or whether they were stuck in a way that when they got unstuck, they would produce a very big earthquake. And so it's actually it's remarkable that this is fundamentally a geophysical problem, but a lot of the answers came not from conventional geophysics, but instead from the mud of estuaries, from the rings of trees, and from old Japanese documents. And so in that way, it's a very nice story that it was geophysicists who set out the problem, who defined the problem, okay? And so they, in a way, told the geologists what the question was, and made it easy for us to then go out and see what had actually happened here. But it was left to the geologists to extend history farther back into time so that we could learn what nature is capable of doing here. For subduction zone earthquakes, as was shown with the 2004 Sumatra Andaman, or the Indian Ocean tsunami of 2004, people said nothing like that's ever happened before. And what does that mean? What sort of time frame are they looking at? Did they extend their time frame far enough back that on a time scale appropriate for the repetition of these very big earthquakes? It takes a long time for them to incubate. Well, geological clues on the occurrence of these very big earthquakes come largely for our subduction zone from the land level changes that accompany the earthquakes. And this is just a matter of the overriding plate riding up a ramp over the fault rupture shown in the rupture area in red, a little bit down into the pink. And so that's giving you the uplift just because the plate's moving up the ramp. But then back here, the rocks are getting stretched like a rubber band. They get thinner, and the land surface drops in a broad warp, down warp, that might be 1 or 2 meters deep, but many tens of kilometers across. So entire coastal estuaries get to enjoy the same lowering of land. And if you can just go canoeing around, as Scott said, and you keep seeing in the banks the same story. It's a very different situation than digging a trench across the San Andreas Fault, where you have to dig a trench across the fault, right? Here you're on top of the fault, but because of this, the land level changes are so extensive, you can look in lots and lots of places, and it makes a big difference. It made this detective story very easy to solve on the North American side. So what does the land level change do for everybody knows, I'm sure you've seen this stuff, that the trees that are living dangerously close to tidewater before the earthquake when the land drops a meter or two, they end up being covered, having the forest floor covered by tides afterwards. And then the tides bring in mud, and that builds up the mud around the trunks of the trees, and eventually you set up with a marsh that's ready to record the next earthquake, and with enough time you might get a forest out here. An example from southwestern Washington state, the trunks standing up here, and then this big one here with some people for scale. These are the trees are western red cedar, which is particularly durable. So its trunks haven't rotted away. The trunks haven't fallen down. These have been standing dead for 300 years, sticking up out of a brackish water tidal wetland. Now, Scott mentioned the work of Kurt Peterson in Oregon, responsible for most of these yellow dots here. And there were Canadian scientists, Pierre, Gary Carver, and others working in Northern California. There were outsiders as well. They came from Colorado. They came from Great Britain. And they didn't all get along. And so that's probably a good thing, because there were good, science is a pretty competitive game, and you want to gun the other person down if you can. But I think they for the most part, they reached the same conclusions about these land level changes and about the sand sheets that represent tsunami. Okay, so in cross section, here we have a bank that stands about 2 meters high. The trees behind are on a forested upland, okay? And then there's a bench here that's the surface of a modern salt marsh, but we're down low enough in the tide creek that we can't see across the broad surface of the marsh, but there's its edge. And down about a meter below the surface are the roots of Sitka spruce from a forest that was lowered into tidewater here. Just around the corner are the remains of a Native American fishing camp that was also submerged as a result of the subsidence of the land that allowed the tides to come in. So then the tides have built this mud back up and constructed that marsh, right? And then here, from about the year 400, give or take 20 or 30 years, another line of spruce roots from an earlier earthquake. So that's one kind of recorder. And then sometimes with that recorder, you get evidence for tsunami. And it's just that the tsunami, is generated by remember the picture of the plate going up the inclined, up the ramp, right? And the seafloor getting kicked, essentially, and generating the tsunami. But at the same time, the farther inland, the plate is getting stretched and the land is dropping. So at the time that the land level change takes place along the coast, a tsunami is being generated offshore. And the tsunami comes in within tens of minutes, and it finds the shore freshly lowered, makes it easier for the tsunami to rush across it. It can suspend sand and leave behind if it's got a good source of sand and a good place to leave it. It can leave behind a stratigraphic record of the tsunami having come in. So here's an example from Willapa Bay, and the fossil stuff is all dark here. The green is a modern analog for this right here. This is a grass, Deschampsia caspitosa or something like that, a tufted wiregrass or hairgrass, I think are the names for it, common names. But it was rooted on a salt marsh surface or brackish marsh surface here on the night of the 26th of January, 1700. And then in came a tsunami from left to right. Inland is to the right. And all the grasses we've been able to dig out in this bank all show this flop over direction up valley. And then the little notches here are places that had sand grains before I threw buckets of water at the outcrop. and that teased out the sand grains but left the mud, so the sand becomes recessive and looks dark. And the simplest interpretation, I think, is that each of these recessive layers represents a different wave in the tsunami train. And this estuary in Willapa Bay is so muddy that there's time for mud to fall out in between the waves. Okay, so that's a second clue.